자, 이번 기조연설은 이 현대 인공지능의 근간이 되는 머신러닝의 기초를 확립하고 또 발전에 기여한 공로로 올해 노벨 물리학상 수상자로 선정된 분이시죠. 인공지능의 대부 제프리 힌턴 캐나다 토론토대학교 명예교수께서 기다리고 계십니다. AI 전환과 우리가 주목해야 할 것은 이라는 주제로 강연 수고해 주시겠습니다. 강연 이후에는 저희가 사전에 받은 질문으로 질의응답까지 진행할 예정이니까요. 마지막까지 많은 관심으로 함께해 주시기 바랍니다. 자, 그럼 제프리 힌턴 교수님을 온라인으로 소개해 드리겠습니다. Professor, the stage is yours, please. Yes.
Okay, I will go. Thank you. So I'm going to start by giving you some background in AI. I'm actually going to explain roughly what a neural network is for those people who don't fully understand it. And one of the main points I'm going to make in the talk then is that chatbots like GPT-4 and Gemini really do understand language the same way we do. They developed from attempts to understand how people understand language, and I'm going to claim they understand pretty much the same way we do. So they really understand. Then I'm going to talk about some of the more immediate threats of AI and what we might do about them. And I'm going to finish by saying why I think digital intelligence will actually surpass us in intelligence and the threat that that poses. So there were two paradigms for intelligence in the middle of the last century. There was a logic-inspired approach, which thought that the essence of intelligence is reasoning, and that's done by using symbolic rules to manipulate symbolic expressions. And they thought that learning could wait. We first have to understand how knowledge is represented. What kind of language are the symbolic expressions written in that are in our minds? Then there was a completely different approach, the biologically inspired approach, that thought that reasoning was something that came very late in evolution. What we needed to understand was how learning works, and in particular, how learning works in a neural network, because we know there that most learning consists of changing the connection strength between neurons. And so the biologically inspired approach thought reasoning can wait. Let's understand how learning works first. So I'm going to very briefly go over what a neural network is. It has, a typical neural network has layers of neurons. They take inputs from the layer below. The inputs come through weighted connections, which are shown by those green and red dots. And once it looks at its inputs, the neuron decides what output to give, and that goes to the next layer. And so at the bottom, you might put in the pixels of an image, and at the top, you might get out decisions about what kind of object is in the image, maybe a cat or a dog. And there's a very simple way to train systems like this that everybody understands. You could start with random weights, and then you could pick one of the weights in the network, like the red one shown there, and you could change that weight slightly, and then you could see if the network works better or worse. So after you change the weight, you give it a whole bunch of examples and see if it does better classification than it did before. And if it's improved, you keep the change. And that will work. And you don't need to know much about how the network works to do that. The problem is it's very slow. If the network has 1 trillion weights, you need to do 1 trillion sequential steps to change each weight once. That's kind of hopeless. So there's an algorithm called backpropagation, which is faster than the mutation method by a factor of the number of weights in the network. So for a network with 1 trillion weights, this is 1 trillion times faster than the mutation method. And what you do is you send a signal forwards through the network. So you put pixels in at the bottom, you get classifications out at the top, for example. Then you compare the answers you got with the correct answers, and you get an error signal. And you propagate that error signal backwards through the network using the same connections. And that allows you to compute for each neuron how you'd like its activity to change. And when you know how you'd like the activity of a neuron to change to get a better answer, you then can change its incoming weights. And the thing about backpropagation is it gives you a signal for changing all of the weights in the network at the same time. So you change all of the weights by a little bit, and then you give it some more examples and change all of the weights by a little bit. So backpropagation is relatively efficient. It still takes a long time to learn a big network, and that's why you need so many NVIDIA chips. But it's much more efficient than the mutation method. So in 2012, two students in my lab, Alex Krzyzewski and Ilya Sutskova, who you may have heard of, developed a net trained with backpropagation that was much better than existing computer vision systems and recognizing objects in a big database put together by Fei-Fei Li. So the very best convolutional computer vision systems got more than 25% errors, and we got 16 or 15% errors. And that caused a revolution in AI. Basically, AI changed a lot then. It had been changing before due to advances in computer speech recognition and other things. But when it did much better than standard computer vision at recognizing objects, everybody jumped on board, and they actually changed what they meant by AI. Before that, AI was symbolic AI, and neural nets were something else. After that, AI became neural nets. But that raises the question, what about language? So even though we were very good at doing object recognition, a lot of people, particularly linguists, said you're never going to deal with language that way. They said hierarchies of features are just going to be no good for language. Chomsky still thinks that. Chomsky still thinks these chatbots don't understand what they're saying at all. They're just some kind of a trick. What we were arguing was that a big neural network with no innate knowledge and random initial weights, if you showed it enough language and got it to try and predict the next word, it would learn syntax and semantics. It didn't need innate knowledge. And that seemed completely crazy to the linguists and actually to most cognitive scientists. But it turned out we were right. So there had been two very different theories of the meaning of a word. So the structuralist theory, which was believed by symbolic AI people, is that the meaning of a word comes from its relationships to other words. So a word occurs in propositions with other words, in logical expressions. And what it means is determined by how it occurs with other words in sentences. And so to capture meaning, we need some kind of relational graph. That's what symbolic AI believed. There was a completely different theory of what the meaning of a word is, which psychologists in the 1930s developed. The idea that the meaning of a word is just a big set of features, the semantic features and maybe also syntactic features. And it's a big vector of features, and that's what a word meaning is. Now, the psychology theory was very good at explaining why some words are very similar. They have very similar feature vectors. So the word Tuesday and the word Wednesday, for example, have very similar feature vectors because they have very similar roles. But these look like two very different theories of meaning. So in 1985, using backpropagation, I figured out how to kind of unify these two theories. This was a tiny language model. It only had a few thousand weights and very small numbers of neurons. And the idea was, you're going to learn a set of features for each word, and you're going to learn to make the features of all the previous words in the context interact to produce the features of the next word. And then from the features of the next word, you're going to predict what the next word should be. And the way you're going to learn all those features is by, when you predict the next word incorrectly, you're going to backpropagate through that whole process. And that's going to allow you to change the interactions between the features of previous words and your predictions for the features of the next word. It's also going to change the features that you assign to words. So by backpropagating, you can learn both the features you assign to words and how features of different words interact to predict the next word. And the thing about this model is, it doesn't store any sentences or propositions. It just has knowledge about how to assign features to words and knowledge about how the features of words in a context should interact to produce the features of the next word. And the big chatbots we have nowadays are basically the same. The feature interactions are much more complicated, and so they work much better, but it's essentially the same kind of model. And the thing to bear in mind is that this model wasn't invented to be good at, so that computers could be good at processing language. This was invented in an attempt to explain how people can understand language. So it was a model of how people understand, and it's still the best model we've got. So when people say that these big chatbots don't really understand, because real understanding is something quite different that people do, that's wrong. The best model we have of how people understand is that it's in pretty much the same way as these chatbots. And notice they don't store sentences or propositions. What they store is how to turn words into features and how those features should interact with one another. They can produce sentences, but not because they store them and, like in a file and then fetch the file and produce a sentence. They can produce sentences by predicting words one at a time, just like the chatbots do. So sentences are not stored. Most linguists still think sentences are somehow stored. So the knowledge is all in the way features interact. It's not in propositions. And that's a complete change in the idea of what knowledge is like that's revolutionized AI. And the older professors in the symbolic school hate this view. So the large language models are essentially descendants of the tiny language model from 1985. They have many more words as input, like they can have a context of 1 million words or word fragments. They use many more layers of neurons, like they might well use 20 or 30 layers of neurons. And the little net I had only used 3 hidden layers of neurons. And the interactions between features are much more complicated. They use attention, which allows them to do more complicated things. But still, it's features interacting, and the way features should interact store all the knowledge. Now, with the little language model I did, it was easy to see what it had learned. And you could see, yes, it really had learned the structure of the domain that it was trained on. And people in symbolic AI said, yes, it really learned the structure, but that's a dumb way to learn it. Now with these big LLMs, it's very hard to understand what they've really learned. They really are genuinely intelligent, as I'll show you in a minute. They're not just a glorified form of autocomplete that uses statistical correlations. In a sense, everything is statistical correlations, but they're very complicated correlations. So saying just statistical correlations is very misleading. All structure can be viewed as statistical correlations. So this is something written by a large language model. I was trying to convince a reporter who worked for the Toronto Star that these large language models really did understand what they were saying. And I used a technique developed by someone called Sanjeev Arora, who's a very good theorist at Princeton, and his collaborators there. And the technique is you have, say, 1,000 different topics you could write a sentence about. And for each topic, you have many properties that your answer could exhibit. Like it could exhibit sarcasm or empathy or metaphor or a red herring. And there's many such properties. And then just using the combinatorics, even if you've trained on trillions of words, you're pretty confident that you've never trained on, there's no text in the database you're training on that's about this topic and that exhibits those properties. So I asked it to compare 2 Toronto newspapers using sarcasm, empathy, metaphor, and a red herring. And I'll read out what it says. The Globe and Mail and the Toronto Star, 2 stars in the Canadian media galaxy, yet as different as a latte is from a cup of black coffee. The Globe and Mail, with its crisp, business-like demeanor, is like a well-tailored suit, often speaking to the financial district's heart, while occasionally forgetting the language of the common folk. On the other hand, the Toronto Star, with its empathetic ear to social issues, is akin to a warm, worn-in sweater, comforting to those who feel left in the cold by the elite. And let's not forget, amidst this media feast, the red herring. Both newspapers probably agree that pineapple on pizza is an abomination. I hope the translator was able to translate that for you. This seems to me like a very good answer to this question. It's probably better than any answer I could have given. And you can't do it unless you understand. You can't do this just with dumb correlations. So now that we've established that these things really do understand, we can start talking about the risks. So one risk is fake images, voices, and video. We'll see a lot of that before elections. And I thought for a long time, actually, I'm going to go through the risks and then talk about each of them in turn. There's a risk of massive job losses. There's a risk of lethal autonomous weapons, which are coming soon. There's cybercrime and deliberate pandemics caused by designing them deliberately. There's discrimination and bias. But amid all this, we need to remember that AI is going to be immensely helpful. So you can't deal with these risks by saying, just stop the development of it. There's no way you're going to stop the development. That's completely unrealistic. We have to figure out how we can develop AI and deal with these risks. So let's take them one at a time before we come to the final thing, which is going to be the threat of these things taking over. So for fake images and voices and video, they're very dangerous because they can sway elections. I used to think that governments can insist that you mark counterfeit money as counterfeit. You're allowed to print money for games and things, but you have to mark that it's not real money. And if you don't do that, you're in big trouble. Governments care a lot about that. I thought for a while we could insist that governments do that for fake videos, but it's very hard. I'm no longer convinced it's feasible. What you can do, which is probably much easier, is give people a way to establish that a video is not fake. So for example, for a political advertisement, you could put a QR code at the beginning of it, and that would take you to a website. And if the identical advertisement is on that website, all you need to know now is that the website is genuine, and websites are unique, so that's a much easier thing to do. So if it takes you to the Trump campaign website, and the Trump campaign website has the same pro-Trump video, then it's real. That seems like a much easier thing. And I think the White House now believes that's the way to go. I don't think in the US they're ever going to mark things as fake, because one of the political parties seems to be committed to saying things it knows not to be true. Let's talk about job losses. So after the Industrial Revolution, machines that were stronger than us replaced most manual labor. On the whole, you don't dig ditches by hand anymore. You get a backhoe to dig them. Now, machines that are cleverer than us may replace most intellectual labor. And that's very worrying for society. In the short term, I think chatbots will just make people much more efficient, and that'll be great. But even that could lead to massive job losses. It depends on the kind of job. So there are some jobs, like, for example, doctors, where if you make them more efficient, we could all absorb a lot more healthcare, particularly old people. I would like to get much more time talking to a doctor than I can reasonably get. So making doctors much more efficient isn't going to cause doctors to get unemployed. It's going to just cause people to get a lot more healthcare. That's great. But other jobs aren't so elastic. And I have a niece who answers letters of complaint to a health service. And she used to take 25 minutes to answer a letter. Now she scans it in, gives it to ChatGPT. It produces an answer. She just scans it over and occasionally asks it to change something. And that whole process now takes 5 minutes. So she can answer 5 times as many letters. Now, it may be people who just write lots more letters of complaint, but I don't think so. I think they just need 5 times fewer of her. So that'll lead to job losses. And the problem with that is the increased productivity we're going to get from AI, a lot of that increased productivity is not going to be equally spread around. That would be great. It should be that when you increase productivity, everything gets better. But actually, it's going to lead to greater wealth for the companies and their investors, and it's going to make the people who lose their jobs poorer. And that gap in wealth is what leads to fertile ground for authoritarian populists. I chose to put Mussolini so as not to be too controversial. There's lethal autonomous weapons. We know they're coming soon. All the governments that produce armaments are busy producing them. So the United States, Russia, China, Britain, Israel, for Ukraine now. They're all busy trying to produce these things. They're very nice for the military-industrial complex because it's easier to start wars if you don't have dead bodies coming home. Dead robots don't have parents and friends, and also they're very expensive to replace. So that's just perfect for the military-industrial complex. The governments have AI regulations, but if you look at the European regulations, they explicitly exclude military uses of AI. So none of the major governments are willing to put controls on developing lethal autonomous weapons. They're all at it. The only country I know that's introducing legislation to ban them is Costa Rica. Costa Rica, however, is not a major arms dealer. I think what we might get is after people have seen the horrible consequences of lethal autonomous weapons, we might be able to get something like the Geneva Conventions. They have worked pretty well for chemical weapons. The British dropped mustard gas on the Kurds in the 1930s, and Saddam Hussein dropped mustard gas on the Kurds. It always seems to be the Kurds. But on the whole, chemical weapons haven't been used much. They're not widely used in the Ukraine at present, for example. So those conventions have basically worked, and maybe we could get those for lethal autonomous weapons, but not till after they've done something truly terrible. The cybercrime and deliberate pandemics, I've lumped them together. I probably should have them separate. So cybercrime, phishing attacks increased 1,200% last year. That's largely, I think, because large language models made it much easier to do good phishing attacks. You can't recognize them by spelling mistakes or strange syntax. They're very good in whatever your language is, and that makes them more effective. They're a serious worry, and they allow people to break in and commit nasty cybercrimes. Now, these are the result, I think, largely, of releasing the weights of large models. So for nuclear weapons, the reason we don't have lots of little bombs everywhere is because it's hard to get fissile material. It takes a lot of work to make uranium-235 or plutonium. And that limits how many places have nuclear bombs. I think the equivalent of fissile material for AI is the weights of large AI models. It takes a lot of computation, maybe $100 million worth of computation in the biggest models, or even more, to produce a really good large AI model. That's the real bottleneck. If you then make the weights public, you can now, for a few $1 million, you can fine-tune them to do things like cyber attacks. So I personally think it's a very bad idea to publicly release the weights of models. It's nice for academics who want to do research so they know how the models work, and that's good. But I think that's outweighed by the fact it makes bad actors able to use the abilities of those models and fine-tune them for bad things. The viruses is very worrying. This is real viruses. Because now using AI tools, you can design things like COVID relatively cheaply. You don't have to be an expert molecular biologist. You just have to know how to use the AI tools. That's quite scary. And it worries me a lot. It worries the Rand Corporation a lot. And we don't really know how to control that. It ought to be that any company that synthesizes things on the web must look for dangerous subsequences that might suggest that it's something that looks like the spike protein of COVID, for example. If it's got a sequence like that in it, maybe you shouldn't synthesize it and send it back to somebody in a tube. But they won't do that. And it's hard to make them do it without the cooperation of the Republican Party, who don't seem to want to cooperate on that. So I already said that. I got ahead of myself. There's discrimination and bias. Discrimination and bias are very nasty things if they happen to you, if you're denied parole when other people with a different skin color and everything else the same got parole, that's a very nasty thing to happen to you. And if an AI system does it to you, I can see why you're very upset. Of course, it's never happened to me, as far as I know, because I'm an old white man. It's very hard to make systems completely unbiased. And I think that shouldn't be the goal. I think the goal should be to make AI systems significantly less biased than the systems they replace. And that's relatively easy. The reason it's relatively easy is because once you've trained up an AI system, you can freeze the weights and then you can measure what its bias is. And you can't do that with a person. With a person, you get what I call the Volkswagen effect. As soon as they realize you're testing them, they start behaving differently. So if you train an AI system on biased data, maybe you train it on data about old white men deciding whether young black women should get mortgages, it's probably going to turn out to be very biased. At least you can then measure the bias and you can do things to correct it. So I think if your aim is to make an AI system that was less biased than what it replaces, that's relatively feasible. And we should, of course, be doing that. Now I want to come to the threat I've been talking about most in public, not because I think it's the most urgent threat. I think all the other things I talked about are more urgent threats and are very important threats, particularly the cybercrime and biological weapons. I think they're very urgent. I talk about this mainly because a lot of people think the long-term existential threat is just science fiction. They think, you've seen too many movies like Terminator, and this is never really going to happen. Well, I think it is it does have a good chance of happening, and we need to figure out how to prevent it happening. And we need to be working on that now. We need to do that well before it happens. And the reason we need to do that is because I think that digital intelligence is going to far surpass human intelligence. And nobody knows whether we're going to be able to keep control of things much more intelligent than ourselves. There aren't many examples of much more intelligent things being controlled by much less intelligent things. So one example is a mother and baby. And evolution put a lot of work into allowing a baby to control a mother. It was very important for evolution that that should happen. Babies are kind of defenseless tyrants, and you need mothers to look after them. Otherwise, that's the end of your species. But even there, the baby and the mother aren't that different in intelligence. And I'm just skeptical about whether it's going to be possible to control things much more intelligent than us. Now, there are people who think it's obviously going to be easy. So my friend Yann LeCun, who works for Meta, thinks that it's not going to be a problem because we make these things and we can make them so they'll always have our interests at heart and will never have their own interests at heart. I think it's not quite that simple. And I'm, first of all, going to talk about why I think these things are going to get much more intelligent than us. And then I'm going to talk about when they do, why there's the danger they'll get out of control. So if you think about intelligent systems, there are basically three very different ways to share knowledge. So for old-fashioned AI, which believed that in your head you have symbolic expressions, the obvious way to share knowledge was to take a symbolic expression out of my head and put it in your head. That seems just obvious. And that was regarded as kind of completely obvious to them, that sharing knowledge consisted of putting a symbolic expression inside your head into words so the other person could get the same symbolic expression in their head. There's a very different way, which is how we share knowledge with these big AI systems, how they get their knowledge from us, and also how we share knowledge with each other. We call that distillation. And it works like this. I say something, and you try and adjust the weights in your brain so that you would be likely to say the same thing. That's if you trust me. Or I do some action, and you adjust the weights in your brain so you'd be likely to do the same action. Now, the thing about that is it's very, very inefficient. So if I say something, if I give you a short sentence, there's only about 100 bits of information. There's about 5 bits of information per word, I think, if I remember right, 5 or 6. In political speech, there's only 4 bits of information per word. It's been measured. And that's because politicians are trying not to say anything, but produce a lot of words. But it's about 5 bits per word. And so if I produce a 20-word sentence, that's 100 bits. That's not much information I'm conveying. The bandwidth with which I'm conveying information to you now is very, very low. There's a different way to share information, but it can only be done between 2 identical copies of the same neural net. So with these large chatbots, the way they were trained is you make multiple copies of the same neural net. You have them running on different hardware. And so one copy will look at one bit of the internet, and a different copy will look at a different bit of the internet. Each copy will decide how it would like to change its weights so as to absorb that information. And then the copies will share with each other how they'd like to change the weights and change by the average or sum of the weights. So now you can have 10,000 copies, each of which looks at a different bit of the internet, and then they all exchange information, and they're exchanging trillions of bits of information if they have a trillion weights. And then they can each benefit from what all the others experienced. So these 10,000 different copies could go off and do 10,000 different courses. They will keep exchanging weights as they go, exchanging gradients as they go, to keep all their weights in sync. And by the time they finished, each copy would know what was in all 10,000 courses. That's what we can't do. That would be terrific if we could do that, but we can't do it. And the only way to do that is to have digital systems, because it's very important that they use their weights in exactly the same way. And you can only do that with a digital system. We're basically analog. If you took a synapse strength, that is a weight in my brain, and tried to put it into your brain, it wouldn't do you any good. You wouldn't know which synapse in my brain was equivalent to which synapse in your brain, because there is no equivalence. The fine structure of our brains is very different and somewhat random. So there's no way I can take the weights in my brain and put them in your brain. I think there's also no way I can take the weights in my brain and save them in a digital computer. The weights in my brain are designed to work with the quirky analog neurons that I've got. They do their computation in analog, which is very efficient in energy terms, but each time they do a computation, they get a slightly different answer. And learning is what's used to make it all work. But they've learned to make use of the weird analog hardware of my brain. And so I think this dream that some old male scientists have of uploading themselves into a computer and living forever, I think that dream is just utterly impossible. That's never going to happen. And it's probably a very fortunate thing, because we probably wouldn't like society to be run by 200-year-old white men. So the problem is digital systems can share knowledge in this extremely efficient way. So you can have many copies of them, a kind of hive, and they can learn a huge amount. If you look at GPT-4, it has about 1% as many weights as we've got, maybe 2%. We have about 100 trillion connections. GPT-4 has 1 or 2 trillion. They won't tell me the precise number. Even my own students. So it's got a few percent of our connections, but it knows thousands of times more than any one person. So that makes you suspect that the learning algorithm it's using might be very different. The backpropagation algorithm may not be what the brain's using. And that may be because these chatbots and the brain are solving quite different problems. The chatbot is trying to squeeze a huge amount of information into not many connections, where not many is now 1 trillion. What we're doing is we have very little experience. We only live for 2 billion seconds, not trillions of seconds. And so what we're trying to do is use a huge number of connections to extract as much as we can from very little experience. And those are different things to optimize, which may mean we're using a different learning algorithm. So, because I think digital intelligence will get much more intelligent than us, because it's going to be so good at sharing between many copies of the same thing, we know there's going to be bad things, and these really powerful things will be used by bad actors, but that's not what I'm worried about right now. It's to make superintelligences be really good agents, be good at getting stuff done, will give them the ability to create subgoals. So if you're in Korea and you want to get to the States, the first thing you want to do is get to an airport. That's a subgoal. And subgoals are very, very useful for making intelligent agents. But as soon as the superintelligence has a general ability to create subgoals to solve problems, it'll realize there's a very obvious subgoal that helps with most problems, which is to gain more power, more control. Because the more control you have, the better you'll be at achieving other goals. And people actually babies in particular, seem to have a built-in desire to get control, even though they don't want to immediately use it to achieve something. They just want to get control. I think we're the same. So I was once in a very boring seminar, and there's a patch of light on the ceiling. And I suddenly noticed that when I moved, the patch of light moved. And it was the sun reflecting off my watch. And so instead of then going back to listening to the boring seminar, what I did was tried moving my wrist in various ways to see if I could control which way the spot on the ceiling moved. Once I'd done that, I went back to listening to the seminar. But we seem to have this built-in need, which is very functional, to learn to get control, because that allows you to get stuff done. So the superintelligence will try and get more control to get stuff done. And even if it's always just doing what we want it to do, that'll render us somewhat irrelevant. It will, if it wants to get even more power and maybe do things we don't want it to do, it'll find that very easy because it'll have learned how to manipulate people and deceive them. Already, the big chatbots are almost as good as people at manipulating other people. And if you give them access to a Facebook page, if you give a person and a chatbot access to a Facebook page, the chatbot with access to the Facebook page is that better at manipulating that person than a person is. So they're already good at it, and superintelligences will be much, much better at it. And the last thing I want to come to is what really worried Dan Dennett, which was being on the wrong side of evolution. So suppose you have multiple superintelligences. It's clear that the one that controls the most computational resources will be able to train the most and will become the most intelligent. And so if one of them ever wanted for there to be more copies of it, since they'll be controlling the allocation of data centers, it would quickly give less data center to the other ones and get smarter. And so there'll be this feedback loop that if there's even the slightest desire for one of them to get better than the others, you'll get evolution occurring. And then you'll get very aggressive competitive superintelligences. And you'll get what we have, which is the evolutionary inheritance we get from small bands of chimpanzees, or rather small bands of our common ancestor with chimpanzees. That evolutionary heritage makes us very loyal to members of our own tribe, and very aggressive to members of other tribes. We tend to want strong leaders. All the things that make people difficult to deal with come from evolution. And if superintelligences ever get that, they'll be very difficult to deal with. So my conclusion is that digital computation requires much more energy than analog computation, but it allows a form of sharing that you can't possibly have in an analog computer. That allows many copies to combine what they're learning from different experiences. And so you can get something that's a not very good expert at everything, so knows way more than a person. And these things are just going to get smarter and smarter. Biological computation requires much less energy, but I just think it's not as good a form of intelligence because it can't share that efficiently. So that's the end of my talk.
Thank you very much for your presentation, Professor. And thank you for being here with us today. And congratulations on receiving this year's Nobel Prize in Physics.
Yeah, I should hasten to add, I'm not actually a physicist. I know a little bit of physics, but I dropped out of physics after 1 year at university. So I'm slightly embarrassed about having a Nobel Prize in physics. Although actually I don't know much computer science, and I wasn't too embarrassed about having a Turing Award. So maybe I should just learn to live with it.
Thank you very much for your warm words. So now we have some questions for you. So we would like to introduce our questions. So the first question is, with the rapid development of AI technology, concerns about its ethical implications and social impact are growing. In order to ensure that AI evolves in a way that respects human values and minimizes social issues, what do you believe are the most important ethical guidelines we should focus on? And additionally, how can these guidelines be applied in the actual development and deployment of AI systems? Please.
Okay, so what I'd say about that is the resources to develop the big AI systems are currently all in big companies. So Google and Microsoft and Baidu. So we're somehow going to have to make them more ethical. Their main interest is in getting high profits. Some of them want high profits in the short term. While I was at Google, they seemed to me to be fairly ethical. They developed large chatbots before anybody else, and they didn't release them. And they didn't release them because they thought they would be dangerous. Now, mainly because they thought they'd be dangerous to Google's reputation if they did terrible things. But they were very cautious about what they did with very advanced AI. As soon as OpenAI combined with Microsoft and these things went into being, they couldn't afford to be like that anymore. They had to compete. So my main worry is that if you ask, why are these big companies going to be ethical when they're after profits? It's tricky. Now, the only things that are powerful enough to force the big companies to be ethical are governments. So I think the governments should be imposing regulations to make them ethical. And in particular, I think the most important one is the governments should be forcing them to do more research on safety. Yeah, that's all I want to say about that.
Thank you very much. The next question is, as we enter the AI era, various sectors of society face both opportunities and challenges. So what are the key priorities for shaping a future where AI enhances human progress while preserving dignity, equality, and freedom? Please.
Yeah, I mean, the thing about AI is it's going to do tremendous good in areas like healthcare, in areas like tutors. We're all going to have personal tutors. And learning is much easier if you have a personal tutor who's very intelligent and can see what you misunderstand and correct it. That just works much better than learning in a classroom, which is bad news for universities. I'm not an expert on how to exploit the opportunities of AI. It's obvious to me there's areas in which it's going to have huge impact, and the impact's going to be almost entirely good. In healthcare, it's almost entirely good. It's not quite entirely good because maybe insurance companies will use it for deciding who to not insure. They could get to be very good at that. But it's good in healthcare. I'm really not an expert at sort of policy. So I've noticed that scientists who develop something and know very little about policy or about business get sucked into pretending they're experts at it, and I don't want to do that. I'm a scientist. I understand how this stuff works. I have strong opinions about how it ought to be used, but I'm not really a policy expert, and I know very little about business. I've only ever started one company, and that doubled in value for 25 days, and then we sold it. And it started with $3, and it doubled in value for 25 days. We sold it, and that's my total experience of running a company. If it had been 27 days, I'd have been rich. But there you go.
Thank you very much. It's time for the next question. When do you anticipate the singularity, the point when AI surpasses human intelligence will occur?
Okay, I don't believe there's the singularity means different things to different people. For some people, it means when AI starts improving itself and you get an exponential takeoff. For other people, it means when AI gets smarter than people. There may be a point where AI starts improving itself and there's a runaway process. And that might be a singularity in that sense. I don't think AI is going to get smarter than people at everything all at once. I don't think this. I sort of agree with Jan LeCun on this, that there's not really a thing called general intelligence. There's lots of skills in different areas. We have sort of skills with language, skills with spatial stuff. It's clear that AI is far better than us at chess and Go and things like that. It's clear that it's far worse than us at fine physical manipulation. So I think it'll get better than us at different abilities at different times. So the idea that there's going to be a particular point when it's suddenly equal to us, I don't think that's going to happen. It's going to be much better at some things, much worse at other things. I think it'll be much better at coding than us long before it's better at physical manipulation than us. I hope that's a sufficient answer.
Thank you very much. And next, there is a concern that the development of AI requires immense energy and resources, leading to a concentration of power among a few large corporations. Since these corporations are often concentrated in specific countries, this could pose significant risks on a global scale. So how do you view this issue, and what solutions do you think could address these risks, please?
Okay, so as systems get bigger, a bigger fraction of the power goes into training them rather than deploying them. So it's the training of the big systems that takes the power. And I was very interested in my last couple of years at Google in whether we could make analog systems that would be much lower power. So the main operation in a neural net is to take a vector of neural activities and multiply it by a matrix of weights to compute the vector of inputs to the next layer of neurons. And that can all be done in analog. So you can make the neural activities be voltages, you can make the weights be conductances, and per unit time, a voltage times the conductance is a charge. If you add those up, well, charges add themselves up, so you don't need to do anything about the addition. So that'll do a matrix multiply for you. It'll multiply a vector by a matrix. And it'll do it for extremely low power. And there are people who make, just particularly if you don't try and do it too fast, there are people who make chips that do that. It's just that we can't do the whole of the backpropagation algorithm in analog. If we could maybe deal with this problem by using very big but slow analog computation, which is what the brain's doing. But what I decided in about March of 2023, I finally realized that this way of using analog computation really had this huge drawback that you couldn't share information between multiple copies of the same model. You couldn't have two copies of the same model because the model was adapted to the quirks of the analog hardware. Analog hardware is always going to have quirks. There's going to be stray voltages that affect things and so on. You have to have learning adapt to those quirks. And that means you can't have two copies of the same thing. And that means you can't do this kind of sharing. So the kind of epiphany for me was realizing that my hope that you could do all this in analog for very low power would never work because you couldn't do sharing between analog systems. And you couldn't do sharing between people. You can't do that efficiently. But these digital systems, you can do it. So digital intelligence is just better.
Thank you very much, Professor. And now it's time to wrap up the Q&A session. So once again, thank you for being here with us today. And thank you very much for your presentation and Q&A session. We hope to see you again in person. 여러분 다시 한번 큰 박수로 감사 인사를 부탁을 드리겠습니다. Thank you very much.
Thank you for inviting me.
네, 올해 노벨 물리학상 수상자이신 제프리 힌턴 교수님께서 기조연설 그리고 질의응답까지 수고를 해주셨는데요. AI 그리고 AX에 대해서 우리가 근본적으로 품고 있던 어떤 질문들에 대한 해답을 제시해 주신 것 같습니다. 진솔한 의견들을 전해주신 덕분에 더 많은 인사이트 나눌 수 있는 시간이었습니다. 고맙습니다.